Could one of you confirm that on the YouTube channel, this is being presented? There's no glitch. Let me just verify that. Yes, it is being. So
yeah, it's coming on us.
All right, folks, so let's get started. Welcome again to this course. This is Introduction to Neural Networks.
We can see you on YouTube.
Yes, thank you. Welcome to the Introduction to AI, Artificial Intelligence, as it is called. It's a big topic. Now, this course that I'm offering, just a few ground rules. Everyone is welcome to attend the first 3 sessions. Those of you who would like to participate in a more engaged way, for 3 weeks, you can register for the course portal, you can engage with the learning material and so forth. Now, I'll just just give 5 minutes to the logistics of it. This will happen every Tuesday evening, Pacific time, 7 p.m., and it's open-ended. 2 hours is the formal session, and after that, I'll open it up to question and answers and helping you guys. Now, we will alternate between theory and lab. 1 week we'll do theory, we'll build some foundations. The second week, we will practice what we learned. So we'll do a lot of labs. And then sometimes I'll do a session in which it is a theory in the beginning, explaining the lecture session in the beginning, followed by lab session. Lab means programming and building something with AI, training a model on some data, and so on and so forth. That's how it goes. This course has a course portal, which I would like to show to all of you so that you know where to go for all the. So this is a YouTube channel, of course. Then we have a course portal. Those of you who have already registered for the course have access to it. For those of you who are guests, I can give you access for 3 weeks. Just send me an email and I'll give you an access. When you come to the course portal, go to My Courses, and you should find a course with a robot on it. If you see my screen and if you see the robot, Introduction to AI, Neural Nets, LLMs, and Gen AI, this is the course that you should come to. This course portal should be your go-to place for all information. Now, there is also a Slack channel. Generally, courses that support vectors are very engaged. The cohort, the participants are actively engaged. They keep exchanging messages, they keep exchanging information throughout the week. So and I will post a link to or an invite to Slack on this course portal. I just now noticed I haven't done that. Now, this is the Zoom link. Of course, you guys have come through Zoom. Those of you who are remote, so you don't need the Zoom link. But if you ever do forget, this is the Zoom link. We have suggested 4 textbooks to guide you through. Now, the reason I've given 4 textbooks is everybody's learning style is different and what people expect from the course is different. Some people have background in programming. They want a programming heavy textbook. Some people like to stay at the intuitive, logical level because they want background. They have background in leadership, in management, in product management, in program management, and so on and so forth. Different forms of leadership, non-programming background. We have physicians, we have psychologists amongst us, right? Or we have robotics experts, mechanical engineers, and people from many disciplines. So I've deliberately put 4 textbooks. One of these will certainly cater to your learning style and your background, right? I'll talk a little bit about them. Understanding deep learning is perhaps the one that I would recommend most if you have enough background in computer science. It's an excellent book written by Simon. It just came out, as in January it came out. To the extent that it just came out in January 2024, obviously it is in high demand, it's become a bestseller already. At the same time, 2 things good about this textbook are it has all the latest, most of the latest stuff that has happened. In this fast-moving subject, it's hard to find books that are up to the latest. So this is one of them. Other benefit of this textbook is the author has made all the material of the textbook freely available if you prefer the digital version. So for example, you see the entire textbook as PDF, uh, available as Creative Commons, free open license. You can, of course, order it. You can find the errors in the book here. You can cooperate in helping make this book better by reporting bugs through GitHub. You can have a discussion on Twitter about it. This is the table of contents, and it pretty much covers all the topics that we are going to do in this workshop. Now, if this looks a big list, please do not be intimidated. The whole point of a instructor-led course is to make the difficult easy and intuitive. It's my job to make sure that what looks like an intimidating list of topics becomes for you a very intuitive, easy to follow journey. As Goethe once said, everything that is easy starts out by being hard once, right? So and the goal of this course is to make the hard into easy as we progress through it. Obviously, there are a lot of figures, PowerPoints, and so on and so forth in this course thing. There are slide decks, etc., etc. There are answers to questions. There are Jupyter notebooks, very important for those of you who are programming inclined, who want very practical and hands-on experience. We will be referring to this Jupyter notebooks quite a bit throughout this course. Now, the other textbook along this line says a dive into deep learning. This is again another great book, again completely or freely available on the internet. Its great strength is that it is more programming heavy. It doesn't go into the theory at all. I mean, it does go into the theory, but just about enough theory. It says, let's get started. And how can we get you started easily? If you have even basic background in Python, you're good to go. And there you are. And you will be able to read this book even if you don't know programming or don't want to do programming. It's still a very good book. The third book in this thing is this Deep Learning, Foundations and Concepts. This is a book by Christopher Bishop and his son, Hugh Bishop. So it's a bishop and bishop. For those of you who are from a scientific background, it may interest you to know that Christopher Bishop not only used to head the machine learning lab, machine learning division in Microsoft. I think he still heads some form of machine learning division in Microsoft. He is also a direct student of Peter Higgs of the Higgs boson fame, the God particle fame. Right? So it's an excellent book, but this tends to be a little bit mathematical. Then finally, the last textbook that I'll talk about is Inside Deep Learning. This book is also a very good book. It is code heavy. Those of you who are comfortable with PyTorch and want to go a little bit deeper in the code and build things, I would strongly recommend you this book. It is in full color and very nice explanations and illustrations in this book. Finally, there's a video that I would recommend. 3 Blue, 1 Brown YouTube channel. Those of you who have watched 3 Blue, 1 Brown channel know that these are absolutely excellent videos. It takes tremendous talent to create videos of this high quality. And the gentleman who started this is a Stanford graduate, mathematician. One would have expected he would have gone and done some research, very esoteric research in abstract math. Instead, he felt compelled to, or he made it his mission in life to make math intuitive and accessible to all of us. And in so doing, he has revolutionized, absolutely revolutionized mathematical education. Because to the extent that neural networks and artificial intelligence have to do with topics that require some mathematical background, there are very few other resources that I would recommend as highly as this. It just makes it very easy. Right? So just some resources for you to have fun. Now, in our course, you will notice that there are these things. I would, oh, so let me see it as students would see it, as you would see it. Let me behave like a participant. Okay, here we go. So at this moment, I've exposed only 4 sections here. And the way this course will continue is knowledge will be trickle fed so that you don't get intimidated. Keep an eye on the day 1, day 0, day 1, day 2, day 3. Today is day 0, just the starter, or we will make our first baby steps into the world of artificial intelligence. Now, this course is unlike a lot of the MOOCs and so forth. We actually have live human beings who are teaching you. One of them is actually talking to you. And there are other people. I'll talk a little bit about them. Kate Amon, she's the course coordinator and an engineer who graduated from UC Berkeley. Chanda Lakshmi Narayan is, again, here in the audience. If you look around in the Zoom participants, you'll see him. He's remote. He's in Bangalore. And so if you feel like asking a question at 4 in the night in US time, you can rest assured that your question will be answered at 4 in the night, because Chanda would be awake. Chanda is from Indian Institute of Technology, Bangalore, very reputed place. He's one of the top rank holders in IIT-JEE, and he has done an amazing PhD in a very, very hard subject, quantum field theory.
Wow, that's your.
That happens to be my PhD. Yeah, so he has done, but except that he is far more bright than I am. So he's here in the audience. There's also Patrish Kumar, a young data scientist. And besides that, we have a few more volunteers, people from the previous batch. One of the traditions in support vectors has been that people who finish a course often volunteer to be the teaching assistant for the next cohort, the next batch. So you may find some of those people are here. They will be answering your questions. One of them is Kyle. She will show up. At this moment, she just got married. And so she is on a honeymoon. She should be back. And there's Harini, who is also in the audience, Harini Datla, and there are a couple of others. So we have a total faculty of about 8 teaching assistants, right? And teaching faculty, including me. So you should be in good hands. And I really mean it. The difference between a MOOC and this online Udemy's of the world or the Coursera's of the world is they probably have good content. But what you get here is we will be engaged with you. We would like to see you make progress and will help you no matter which hour of day or night it is. So do reach out to us for help and we'll be there to help you. Now these are the sections. This is the introduction. Now for each section, you'll notice that there will be, so first 3 sections are easy, Journey of 1,000 Miles. It's an invitation to this course. Please read that. Practical tips on AI. One of the things that happens with machine learning, or when people want to learn AI, is one subset of the cohort of the participants are people who have been away from academic learning. They graduated from university 20 years ago, and they haven't really been in the learning stream. And they do want to learn AI very much. The question that they ask is,
Hey, Asif.
yes.
I think is it Patrish Kumar or Kunal?
Oh, actually, the picture is of Kunal, but it's Patrish Kumar, who
Oh,
looks similar. We'll replace his picture, but thank you for noticing it.
yeah.
And Kunal is also joining as a teaching assistant. So the pictures are interchanged. He is there, Harni Datta is there, and Kyle is there, and a few more are there. So we have a pretty good constellation of talent to be the teaching assistants in this course. Anyway, continuing, a lot of people who come back and they ask, do you think I can do it? The first question you have when you come to artificial intelligence is the imposter syndrome. You feel, I don't think I can do it. Oh, I'm from telecom background. I'm from mechanical engineering background. I'm a psychologist. Oh, I'm a physician. By the way, I'm taking real examples of people who have been in this, who have been exactly like you, taking this course for the last 8 years, variations of this course for the last 8 years. We all have imposter syndrome. This field is new. So I would like to say something. First, this field is new for everyone. It is new for me. The things that I'm going to teach you in this course, I have not taught in the previous batch last year. Why? because the field is moving so fast, so very fast, that the curriculum keeps changing all the time. There are people who take this course over and over again every year. Why? Because every time they take the course, they find that it's a new course, that the content has changed. Right? So it is new for everyone, guys. It's not just new for you, it's new for me too. Right? So that is one. Secondly, if it is anything, we have made psychologists into today people who are directors in engineering at Amazon, in AI, data science team at Amazon. We have taken a taxi driver who once came and said, I'm tired of carrying people to the airport who keep talking this computer science gibberish. Is there any hope for me? Can I also become that? I was skeptical. I said, when will you study if you're driving taxi all day? He says, well, when I go to the airport, there's a lot of waiting time in taxis. You have to wait for your turn to pick up a customer, sometimes for a long, long time. And I can read while I'm waiting. That was 10 years ago. Today, he's actually a senior director in one of the FANG companies that I won't name.
Wow.
Of engineering. Another person who was a director of psychiatry came, said, I want to learn machine learning. And do you have any background in it, in programming? No. Do you have a background in mathematics? No. But I did pre-med, right? There was some calculus in the past. The gentleman today has a very successful company, software company of his own. He has had it for a decade now. Right? We have right here, I think in this audience itself, participating at least one surgeon and at least one diagnostician, 2 MDs, right, who are taking this course along with it. We also have young people. We have in the audience people who, one of them is still finishing high school. Right? So it's a wide variety of audience. If there is imposter syndrome, this would be a good time to divest it. It is my responsibility to carry you forward. I mean it. If I don't carry you forward, I have failed you. And we, the faculty in this course, the whole teaching staff, we collectively have failed you. We expect from you 2 things. Could one of you guess what we expect from you? Commitment, time commitment. Give us the time. Give us a chance to teach you. Number 1. And what else do we expect you? We expect an obligation from you, which is unique to the way we teach. You have an obligation to speak up when you don't understand. As an educationalist, it is my responsibility to keep rephrasing things. Trust me, I will not repeat it. I won't bore the rest of the class. There are no dumb questions. There is a saying somewhere on my wall you'll find here, which says, if you ask a question, you look dumb for a day. If you don't ask a question, you remain dumb for a lifetime. Right? So please do ask questions. It's a very interactive, engaging workshop. Right? And we do want you to ask a lot of questions. The whole thing, we have to learn by talking. Going back to Socrates' mode of the teaching, Socrates produced Plato, who produced Aristotle. If you look at those peripatetic philosophers of Greece, Socrates would walk and his students would walk with him and they would be having a jolly conversation. Great philosophy came out of it. Chandrasekhar, one of the great physicists, and perhaps one of my great heroes, he taught a class, graduate school in University of Chicago, which has a unique distinction which I don't believe has ever been repeated in history. He taught a class in the 1960s of a graduate students in which every single student went on to win a Nobel Prize in physics. Wow. Every single student. And they won the Nobel Prize ahead of him. Right? What was his mode of teaching? Very interactive. Obviously, I'm no Chandrasekhar or Socrates, but I would certainly like to emulate the example and like to help you in this journey. It's a very exciting journey. Things are happening every day. And one of the things that I find most interesting in this course that I've been doing now for years, A little bit about my background. I have had a dual background, actually multiple background. I happen to be a computer engineer, a computer scientist, a theoretical physicist, and an educationalist. So obviously, I have multiple disciplines. For the last 30 years, I've been working in the industry in big companies. I started out at projects in NASA, then Siebel Systems, Oracle, worked with startups, Evolve, then joined Cornerstone, now have my own company. And in parallel, I have also been an educationalist. I've been teaching for the last 30 years at University of, various universities, Syracuse University, University of Illinois, Urbana-Champaign, UC Berkeley. I've taught in the big companies, and now, well, you are my new victims. Right? So what it does, all these years of teaching, is it steeps you in educational theory. If I could sum up all that I've learned in education, from theory, from practice, from actual teaching, it is that all of teaching boils down to a conversation between two friends. When it is a conversation between two friends, it is the most efficient form of exchanging understanding. Right? So please treat it like that. I am in no, you are my superior, each one of you, in some or the other way. Some things you know far better than me. And one of my privileges has been to sit here and to learn every day something new in the field, because the field is moving so fast. So every time some student would tell me something I didn't know, and then I go and read about it. So those are the things. Now, if you're coming to learning after a long time, I would advise you to look at this, and I'm done with this thing, and I'll get started right after that, is this. This is hanging. There's some practical tips to get started with learning. Check it out. It will, I think the course portal may be having a little bit of an issue, Hamad. If it doesn't come back, you can look at it. Anyway, we have that. And today we will do some things basic, very basic. Now, the way this course works is that, as I said, stay engaged with the portal. Every single lecture, so this is something important. We not only teach AI, we use AI. This video that you're watching, immediately, by the time it finishes, we also build an edtech platform, edutech, and I believe ours is a state-of-the-art edutech. Why do I believe that? Because I used to be the head of AI research at one of the leading edtech companies in the world, Cornerstone on Demand. A lot of the whole AI platform was my creation. I've stepped out, and I believe I'm creating something better. Right? So this EdTech platform will take this video, immediately create a summary of it. It will then create some question answer forms. It will create a quiz out of it. Stay engaged. See, today you listen to this session. Tomorrow morning, wake up and take that short quiz. It will take you 10 minutes, but it will validate how much you absorbed. It is self-assessment. Nobody is going to look at your quiz score, but by taking that assessment, you know how much you got. It gives you a chance to go back and review, and if needed, go take the quiz again in a couple of days, right? And what I have been told, this is the experience, and I suppose this is a little bit of a bragging. People have told me that after taking the quizzes at support vectors in the courses, they could run circles around the FANG interviewers, right? At least in machine learning, they become so strong, they fearlessly just sail through those interviews. You might not be able to do your lead code interviews, but certainly machine learning, AI, will be a cakewalk for you, right? So take it seriously, do those. As always, remember, if you take a quiz in 10 minutes, it takes us a long time to put the material together, right? So we work any given day much harder than we expect you to work. So with that background, that's all I have to say about it. I would like to take a little pause and then go. And by the way, one of you, if you want to know what is a syllabus, what is it that we are going to cover, just look at, for example, this book, right? Understanding Deep Learning, and look at its syllabus, and you will see that it is We just watched it. I'm not going to repeat it. That's what it is. Now we have 12 sessions, 3 months. We will not have a break. Come long weekend, come short weekend, we will meet. Right? All the videos will be recorded. Content will be extracted. Quizzes will be created. We'll alternate between lecture and theory, lecture and labs. All the Jupyter notebooks will be posted. They will all contain little exercise for you to extend the work done in those Jupyter notebooks. This is only for people who really want to do the lab. If you don't want to do the lab, it doesn't mean that you won't get something out of the course. Literally, for example, the course that we just finished, the boot camp that we just finished in fall of 2023, as of this moment, I know as a practicality, 4 startups have come out of it. Not all members of those startups are coders. Some of them are purely different. Right? So you get out of it whatever you want to get out of it, and engage with the teaching assistants. They will help maximize your return on investment. Right? Once again, I'll conclude by saying first 3 sessions are absolutely free, and for the first 3 sessions, if you want access to this course portal, please send me an email, right, at info@supportvectors.com. We will add you to the course portal, but your access will be for 3 weeks. After that, if you want to continue, and continue only if you like it. It might not be a cup of tea. If you do like it, then of course you're most welcome to continue with this course. Right? Now, that's for the administrative stuff. Any questions? Because I want to get started with AI now, with the actual matter. Any questions from anyone or any feedback, anything that anybody has to say?
Asif, just wanted to let everybody know, I pinged the links for registration and also where you can email for those 3 weeks of access.
Oh, thank you. Thank you, Madhu. And we seem to have a pretty healthy participation here from multiple, at least 3 continents seem to be represented. Wonderful. All right, folks, if there are no questions, I will start now with a blank slate.
Yeah, Asif, I'd raised the hand, so just...
oh, sure, please go ahead.
Quick question regarding the timings, right? So you said initially it could be around 2 to 3 hours. So till what time is it being recorded? Because it just so happens that every Tuesday I have another meeting which goes from 8 to 10. So, but I would like to attend the whole thing. So as if it is recorded, I'll be able to attend that from 8 o'clock.
So, Shashank, the entire thing will be recorded, except at the very end, we open it up to general discussion between the participants. That will not be recorded. That is just to give people privacy for conversation.
Okay, so including the practical sessions will be recorded?
Absolutely. Everything will be recorded. All the Jupyter notebooks will be posted. All the code will be posted. Right? Okay. And in other words, you won't miss. See, by the way, I'll just take a little tangent and say something. See, guys, there are 2 forms. In educational theory, we talk of pedagogy, teaching children. By children means all the way up to college. It's pedagogy. Peda is children, right? Or the teaching of children. If you can summarize what it is to teach children, it is that children have a mind that can absorb information very well. They have a very mind like a sponge. They can quickly absorb a lot of things. They learn quickly. They have all the time in the world. They have no responsibilities, isn't it? If they really want to learn, the time is there. But they have 0 motivation to learn. So you, statistically speaking, so you dangle the carrot and stick, right? The specter of bad grades, you scare them by saying, oh my goodness, your life will be ruined. I'm sure all of your teachers have done that, right? If you don't study and so forth. At the end of it, one way or the other, they study. But adult education is different. Andragogy or adult education is entirely different. It is based on the premise that people who show up genuinely want to learn. But there is a problem. Adults carry multiple priorities and responsibilities. They have their families to take care of, they have the job to take care of, they have their boss to take care of, right? And their social life. And at the end of it, then Netflix also demands time, right? They have to sleep for some time, and then they want to learn something, right? So is it any wonder that the attrition rate for most adult education, for example, for Coursera, if you were to guess, anyone would like to guess what percentage of courses are finished in the likes of Coursera, Udemy, etc.? Anybody wants to guess?
10%.
Yeah. Well, according to the Department of Education in the United States, the percentage is 3 to 6%. Right? It's a deplorable completion rate because, in my view, is designed the way college courses are designed, in small pieces and so forth. We design our entire curriculum on the belief that you guys are busy lives. You'll be missing for a couple of weeks because you have to travel on business. Your family will fall sick. You'll fall sick. Deadlines will come up in work. So every single thing will be recorded. You can, if you miss something, you want to sit with the TA to get one-on-one recap and catch-up sessions, clinic hours. That's exactly what we're here for. We will make sure you don't fall behind. But you have to give us a chance. You have to reach out to us. And again, you have to take out the time. So please do that. Right. And once again, if you want to know what is the syllabus, this is the syllabus. We'll cover all of it, but trust me, it won't be as intimidating as it looks. It will be very easy. So today we'll start simple. That's why I call it day 0. It's not really getting too much into the material, but we'll start with a clean slate. And this is as clean a digital slate as we can have. Yeah, go.
Quick question. Are we going to work only on Python or with Java and Python or something like that? What would be our
yes. So one question here from is it going to be just Python or is it going to be Java and other languages? So the simple answer is we will standardize on Python, only on Python. All the labs in this course will be in Python. Having said that, towards the end, there will be some optional labs in a new language that is becoming gradually dominant in artificial intelligence. It's called Rust. It's an odd name for a language. Rust, which is applicable to the latest and greatest that's happening. So we'll do Python and Rust. And as you notice in the AI world, a lot of the things are named after snakes. One of the architectures you learn is called Mamba, which is a very deadly snake. Right, and so on and so forth. It's sort of the cultural thing in this field.
Asif, before you start, I'm just going to ask the participants, if you do not mind, put your location information in your name, so that will help us to see where you are attending from. The way to do that, click on participants and then go to your name, right click and rename yourself and add the location if you wouldn't mind. You can see how I have done it for my name. That would help us really to understand which demographic you're actually attending from. Thank you.
All right, folks. So we get started now. See, when we think of artificial intelligence in popular imagination, it really took hold a couple of years ago. I suppose in many, many minds, artificial intelligence is almost synonymous with ChatGPT, right? Or Bard or Cloud or something like that. One of these things. It was sort of a happening moment for AI for many people because they could talk to it, they could ask it questions, they could get intelligent answers. But AI has a much longer history. It's a field that has been practiced for a very, very long time. We'll start by asking, without getting too much into what is artificial intelligence, we'll look a little bit of the history for 5 minutes. See, ever since man has been on Earth and has done tools and built things, it has been an aspiration, historically, that we have always tried to create intelligent beings. Having created hammer and plow and whatnot was not satisfaction enough. So in every culture, you find mythologies you find stories, and you find this aspiration to create intelligent beings. For example, in ancient Greece around 800 BC, you have the myth of I believe it is called Hephaestus, which was crafting of mechanical servants and the bronze man, Talos, who would do what you wanted it to do. Right? Likewise, those of you who are familiar with Arabian Nights and the story of Aladdin and his magic lamp, and out of the magic lamp comes the jinn, who would do whatever you ask you to do. Right? And so what is it? Somebody crafts a magic lamp and comes a jinn. Today, maybe you would call the jinn ChatGPT. Right? And it has been there. In the Jewish tradition, there has been the concept of golem. Their tradition says that from clay, some very enlightened and wise men can create a figure, a golem. But beware, golem will do whatever you ask it to do. It's very powerful, but with it comes dangers. If you don't know how to manage the golem, it can create great havoc. If you think about it, those are exactly the questions we are asking today as AI is dominating. We are asking, what happens if we cannot control this AI? Right? What are the attendant dangers in it? Are we looking at human extinction? Imminent human extinction. So these questions go back many, many years, many hundred years, actually. Likewise, so it has been going on. If you look at the invention of the first computing machine, when Charles Babbage designed a machine, and those were the days when mechanical engineering was the pinnacle of engineering. So he conceived of his computing machine made up of fancy gears. The conception was great. Mechanical engineering had not advanced enough to realize that machine properly. And yet, what was the vision that Charles Babbage was carrying in his mind? He was dreaming of artificial intelligence. Right? That was 1843. But Turing, the genius who broke the enigma, while the intent was to break the enigma code of the Germans, his real intent was to create a universal machine. Today, what we call the Turing machine, or more prosaically, we call it the computer, right? And if you observe the movie that has been made on his life, anybody remembers the name of the movie?
The Imitation Game.
Imitation Games, that's right. Imitation Game is literally about AI, right? His dream was to create a machine, and his paper was called Computing Machinery and Intelligence. This is 1950. Right? A lot about what Alan Turing did, as you know, was declassified only very recently at the turn of the century. For 50 years almost, it was a guarded secret. And it was a guarded secret that the Allies had actually broken the Enigma code. Of course, now the movie has the entire narrative about it. In 1956, there was a Dartmouth conference, which we consider often as the point at which people began to work very seriously on AI research. And John McCarthy created the term artificial intelligence in a more formal way. But if you look at the foundation, the mathematical foundations of artificial intelligence, it goes way back. If I have to say mathematically, theoretically, when it started, and different people will pick different dates, I would pick a date which is 1793. The son of a coal miner grew up to a very bright kid, grew up to join and think about certain problems. And he created a process, one of the most powerful workhorses and pillars of artificial intelligence. He created something called the method of least squares. How do you fit a curve to data, or what today you call regression? Regression analysis, for those of you who know that thing. When he did it, he didn't quite reveal it. He used it to predict the location of some planetoid or some heavenly body. It was a grand challenge in Europe. He predicted it with uncanny accuracy, while the rest of the other competitors, they were widely off. how wildly off, just lie down someday, some summer day, look at the sky and see how vast it is. On any given day of the year, any given year, at any place in the sky, that heavenly body would have showed up. He predicted exactly when and where it would show up. It was, I heard a story, which I don't know how true it is, that, so he was very coy about revealing how he did it. So later on, Legendre, the great mathematician, published the paper in 1805 called Method of Least Squares. And then he jumped out of his seat and said, no, wait a minute, I did that first. Right? And thus started one of the most celebrated debates in machine learning community. It's called the prior debate. Who did it first? Today we know that it was done actually both by Legendre and by Gauss independently, along with an American actually, who did it here independently, discovered it. So the roots of machine learning go far and deep. And Galton, who was studying peas and generations of peas, came up with an interesting observation. He found that the children of very tall people or plants are not as tall. Children of very short people or plants are not as short. In other words, they regress, the outliers, children of the outliers regress towards the mean. So he wrote a paper whose title something is like the regression towards mediocrity in hereditary traits or something like that. I forget the exact title. Landmark paper, I invite you to read that. That was 1885. If you wonder why one of the most, those of you who are familiar with machine learning to some extent, if you wonder why one of the most important class of algorithms in machine learning, namely ability to predict a value, what's going to be the temperature tomorrow at noon, right? It's a number. All methods that predict a number are called regressors or regression algorithms. Regression is a negative word, it's the opposite of progression. And yet, for the historic reason is, it goes back to Galton. And it turns out the explanation of Galton's regression towards mediocrity is the same thing that lay at the foundation of regression analysis. And we won't cover a lot of that history because the world is changing so very fast that we will actually catapult literally 100 years from that. Now, in 100 years, AI, or in 50 years since 1950, AI has been through ups and downs. It has been through hype cycles and then AI winters. We certainly are going through a major resurgence. It's a question to wonder whether we are going through a hype cycle. I don't think so. Breakthroughs are happening at a tremendous pace. If you were to ask why breakthroughs are happening so quickly these days, why was it not happening 20, 30 years ago? When we look back, we realize that AI is a beast that needs to be fed two things, principally. It needs to be fed vast amounts of data, ginormous amounts of data, big data, right? At a scale you can't imagine. Today's models, for example, the so-called large language models, they have been fed every single piece of human knowledge derived from thousands of years of human history in every civilization. It has been fed that knowledge. And it has learned from that. It has learned from every single subject that mankind has. So it knows everything that mankind knows. Is data at that scale that it has been fed, and knowledge at that scale that it has been fed. And the other thing that it needs is tremendous compute power to be able to process and understand that data, from data, extract understanding, extract generalizations, ability to create concepts and generalize from data. And that takes such a vast computing power that in very practical terms, just look at the stock prices of some of these companies that make the hardware. It's just skyrocketing, right? So a few years ago, we had neither the hardware nor the amount of data, but whatever data, whatever hardware we had, mathematically, the third pillar of AI is mathematical foundations. And their researchers have been doing an incredibly good job in taking the field forward. Right? So it takes great mathematics, great amount of data, great amount of hardware to give birth to this baby that is contemporary artificial intelligence. So with that background, I would ask this question. We all throw around this word artificial intelligence. And sometimes when I watch the pundits talk about what is artificial intelligence, you hear statements that makes one cringe. One person, for example, on radio show said, oh, artificial intelligence is the new thing. It completely obsoletes machine learning. Right? Another guy said machine learning, oh yeah, and statistics, just forget about it. Nobody should ever take a course in statistics anymore. Right? These are real statements. These are not exaggerations. I hear from people. There are people who say generative AI has made all other AI redundant or ineffective. It's the new thing. It solves every class of problem much better. So you can forget about everything else. Just learn about a large language model. So leaving that level of deep ignorance, that is, it's shocking that people even make this statement. I suppose it must be the Dunning-Kruger bias or Dunning-Kruger effect. The less you know, the more confident you feel and go about talking. But for some reason, too much of this is going on these days. So I'll ask this question. What is artificial intelligence? And again, like today is lecture 0, it is atypical. Our next few sessions will be very practical. We will do code, we'll build models, we'll dissect models. But today I want to stay at the high level and ask big questions, the big topics. What is artificial intelligence? We know what artificial is. Let's unpack that, right? For example, well, this coat is artificial. It doesn't grow on trees. We built it, right? It is artifice. It's of human construction, right? If it's of ingenuity and design, that's artificial. But what is intelligence? Or what is a mark of intelligence? Is my cup of coffee intelligent, for example? Would you call this intelligent? A mug intelligent? Despite the goodness of this coffee, oh, by the way, those of you who are not here in person, you are missing out on really fresh ground coffee and snacks, endless snacks. But anyway, you don't consider a mug intelligent. You don't consider a tractor intelligent or a steam engine or a train intelligent. So the question is, what is intelligence? Anybody? What is intelligence? When do you ascribe intelligence to something? Or let me put it this way in the human context. When do you consider somebody dull or rather deficient in intelligence? Speak up, guys. Go ahead, Bhavin.
Something that doesn't quite have that thinking power or the converse
Ability to think.
Yeah, intelligence is something that is learned, then
Learning intelligence. Okay, so Bhavin says that you ascribe intelligence to things that can think, creatures that can think. So can learn. Now I'll ask this question. It's a good answer. Anybody else would like to answer? Let me make
perceive
it.
and
Go ahead.
perceive and respond to a situation.
Perceive and respond to a situation.
Or
You know, these days, the video cameras outside your building, they perceive an intruder and respond by turning towards that and going boink, boink, boink.
or
Albert,
a system that thinks like a brain.
a system. How would you know if a system thinks like a brain? We don't know how the brain thinks, or do we? So let me put it in a scientific framework, guys. This is a statement ascribed to Lord Kelvin, the physicist of thermodynamics. He said that a subject has not risen to the level of science until it talks in terms of empirically measurable quantities. So science is a study of measurable quantities and the relationship between them, finding of relationship between them. So then, if I frame it like that, can you guys quantify thinking? Like in our conversation, have I thought 10 units of thinking or 20 units of thinking? Is thinking even quantifiable? Do we even have a clue how thinking takes place? Or what is thinking in a scientific perspective? We do know it intuitively. We can see thinking in people's faces, but from a pure scientific empirical field to the extent that science and engineering are empirical pursuits, do we know how to quantify thinking? I ask this while you're pondering over this question. I'll ask this because one of the most legendary companies in Silicon Valley was a company called Thinking Machine. Created by legends, Nobel laureates came to work there. It was before the last AI winter, the last AI hype. They thought they could create thinking machines, till actually one person under whom I had the privilege of taking courses and attending whose seminars, a gentleman named Sir Roger Penrose, wrote a book, Emperor's New Mind. He basically asked this question, do we know what thinking is? And he questioned whether machines can think. He was not liked for many years. I remember at one time I was told, and I don't know how true it is, computer science professors would give assignments to the students to find all the flaws in the argument that Sir Roger Penrose had made. Well, it turns out there are not that many flaws, and the world disagreed with them because Sir Roger Penrose is a Nobel laureate today. Right? So we don't know what thinking is. We don't even know whether it's a classical phenomenon or it's a quantum phenomenon. So we can't use thinking as a measure. And if it is any bit of history, that thinking machine company collapsed. It never delivered on its promise, that legendary company. It broke up into two parts. One part when the hardware part, I believe, was absorbed by Sun Microsystems, the software was absorbed by Oracle. I actually know that group that it became, data mining group or advanced analytics group. Then, now, of course, Oracle then went on to gobble up Sun also. Right? So somewhere in the Oracle are the dead bones of thinking machine. Now, we don't know what thinking is. So what do we mean by, try another definition of intelligence. I'll give you an example. Tell me if this gives you an idea. Imagine that you take small children to a meadow, right? A simplified meadow. In that meadow, and let's simplify it down because we are doing a thought experiment. There are only two species of animals, cows and ducks. Right? So you are in an educational mindset, as all parents are. Have you noticed that the moment you are near children, most people become educators spontaneously, right? So you show this is a duck. Look at the feathers, look at the beak, look at the webbed feet, and look at the small size. That's what a duck is. And imagine those children are 2-year-olds, and they're barely able to grasp all the complex things that you said makes a duck a duck. And then you explain what a cow is. You say, look at that big animal with a swishy tail, horns, right? And this and that. And it's a cow. And the 2-year-olds are still trying to grapple with it. And then how would you know whether it's a cow or duck? You could say, you pick an animal that you have shown them and ask, what animal is this? Let us say that the child identifies a duck as a duck. Do you think the child has learned what a duck is? Yes. Maybe. Is there a reason to doubt that?
It comes to ability to abstract things and apply to a new situation.
Yes. See, the trouble is, if you show the same animal that you have already explained, the child may have memorized it. So what the child remembers is a specific instance of the duck, but doesn't understand. You don't know, you have no evidence that the child truly can understand the concept of a duck, the duckiness of a duck, or the cowness of a cow. What makes a cow a cow? Are we together? For that, you have to show a completely unseen duck, which differs from the other ducks in some subtle ways, and ask, what is this? And if the child says it's a duck, then you feel maybe the child is getting, but the child may still be guessing. Likewise for a cow. Right? So guys, remember, you have all been through the educational system. How many times when you didn't like the subject, what would you do? You would memorize the answer to 20 important questions and go there and take the exam. So you know that memorization is the antithesis of learning, isn't it? But it creates the appearance of learning. And so you have to take new examples. So that brings in the concept of generalization. You see some specific instances of cows and ducks, but you have to be able to generalize to the unseen instances of cows and ducks and say, they are cows and these are ducks. But when you do that, how perfect do you need to be? So let's measure. How do you measure learning in this scenario? What you can do is, before the child learns, you show the children haven't learned. You show some animals, new animals, and they have a pretty high error rate. They get some right, some wrong, because they're all guessing, isn't it? But then you keep explaining every time they make mistake. You explain a little bit why the answer was wrong. What makes that animal a cow and not a duck? Right? And gradually the children begin to absorb and form a concept. What would be the evidence that they have learned? When asked new questions, shown new samples, they would make less errors, isn't it? The accuracy, the rate of correct answers would go up. It doesn't have to achieve perfection. They don't have to get it right all the time. But the evidence of learning is they make less mistakes. Does it make sense, guys? So now think back at it. Who do you call a fast learner, intelligent person? The person who learns quickly, a quick study. Who do you call a dull person? Somebody you can keep on explaining and giving examples, but is not able to generalize from that. Right? And take it to the asymptotic limit. We don't explain that no matter how much you talk to this cup, it will ever know the difference between a cow and a duck. So you don't call it intelligent at all. So learning is the core, the essence of intelligence. Interestingly, learning is measurable, isn't it, guys? Learning is something that is absolutely measurable. And now I'd like to just write down a little bit and start getting down to brass tacks. See, this now. Suppose you show X. You show X new samples, let's say hundreds, new samples.
We can't see your writing.
Oh, my screen is not shared. Let me share my screen. I apologize.
Yeah, we can see it now.
Okay, thank you. Suppose you show X new samples or new instances of cows and ducks.
Sorry, it flipped again.
Asif, no, we saw it before you did whatever last change you did here. I
Oh.
only see now sign in account into Microsoft.
Oh, I think. Let's try this one now.
Yeah, I can see.
There it is. It's
whiteboard
just
now.
small. If you could increase the size.
Increase the size of what I'm writing? Okay. How about this?
Oh, much better.
Full screen. You won't have space to play.
It's visible. Yeah.
Is it visible now? I thought I made the entire thing, the whole screen visible.
It is. Yeah,
It is visible.
It is.
and
You might not have space. That's all. That's true.
The whole screen. Okay. So, Kate, are you saying that on your screen it's still small?
Yeah.
No. It's nice and big, but now you might have trouble fitting other stuff in, as someone else pointed out. I think Madhu. Yeah.
Okay. Yeah. We'll gradually shrink it once the concepts become clear. But let's take it this way. Let's say
Sure.
you have 100 samples. In the beginning, the children were making, let's say, 50 errors. And now, children, after a lot of explanation, let's say that the children are making about 15 errors out of 100. What would you call this? Is this a measurable way to see learning take place? Isn't it? And therefore, learning is something amiable or something to which empirical sciences can be applied, isn't it? The learning process. But do you notice that learning, the way we have quantified it, if I were to ask, why is it just children? For example, do dogs learn? If you have a dog, you'll immediately shake your head and say, yes, of course. Right? And You see that my dog is certainly agreeing with that every time I say that. Now, amoebas learn, or we have evidence of that. All living creatures learn. But what about non-living creatures? Can a machine learn? And therein is the crux of the word artificial. Artifice, that which we create, the machine, can it learn? If you look at the definition here, there is absolutely no reason to say, well, something says machines can't learn. If machines could somehow magically look at samples, learn to generalize from it, and therefore reduce their error rate in prediction, you would say, well, the machine too is learning. And it is the most miraculous thing. We have learned to endow dead matter, silicon, with its electrons and electron transport equations in semiconductors. Rising from there, from that quantum state, we have worked our way slowly, built this entire edifice of computer science, semiconductor physics, computer engineering, and finally the mathematical architecture that today comes, all these different strands of human pursuit have brought together this thing that we call artificial intelligence. It is amongst the most amazing creations of mankind. It has pretty much to build it has gone all of human knowledge, all of human ingenuity. But today, machines learn. And therefore, the subject, machine learning. Machine learning is the theoretical core of AI. AI has many parts. For example, if you look at the field of AI, let me put it this way. And suppose you take this as a field, let's do a Venn diagram. AI as a field, machine learning is the theoretical core. Its applications, for example, are robots. For example, your self-driven cars and things like that, right? There were other areas like expert systems, etc., which are more or less forgotten now. Expert systems, and there were symbolic systems and so forth, etc. But machine learning is the core. Within machine learning, there are vast amount of algorithms. One of the topics that we'll learn, and today we are staying at a very high level, but you'll learn in the subsequent things, is something which is perhaps one of the most profound contributions of this field to the theory of human knowledge. It is very flippantly or sort of humorously called the no free lunch theorem. Amazing as it sounds, it actually is a deep result. It says that no one algorithm will necessarily always work because the world is filled with different phenomena, different dynamics. Something is controlled by gravitational law, something is controlled by economics, data, the demand and supply rules, physical laws, some are controlled by biological laws and whatnot. Right? Behind every data, see, data doesn't just suddenly appear. It appears because there is a dynamic, there's a causative force behind it that produce the data. You observe some dynamic, some happening, some phenomenon. And in the observation of that, you produce data. So therefore, there's a dynamic. There are some forces at work. You don't know the equations, the relationships that produce the forces. You throw a pebble in the water, it causes ripples. The ripples, as you know, as we all are taught, are governed by sinusoidal laws, sinusoidal function. The amplitude decays as, I believe, either Legendre polynomials or Bessel functions. I forget which of these two, but they are transcendental functions. Right? Every single thing, the hum of the sound data or vibrational data from your airplane is because of the rotation, the spinning of the turbines, and a whole lot of aerodynamics taking place there, right? Fluid dynamics taking place there in the air streams. So data comes from different sources, from different causes. So every algorithm makes a hypothesis about what the force must have been, right? What must have been the real relationship producing the data. That hypothesis may be right, it may be wrong. Right? And so you have to, there's a sort of a democracy of models. The world is filled with many, many models. Each model makes a certain, for example, assumption. Right? For example, you can make an assumption that based on the time of the day from midnight to and temperature to onwards, temperature linearly increases. That would do just fine with a straight line relationship. Broadly speaking, temperature rises linearly, or not exactly linearly, but we'll pretend that it does. And then what happens? It plateaus off and then it starts coming down. So a linear model would have worked here. Maybe would have worked here, but it doesn't work in the entire regime of the data. And so on and so forth. So you have lots and lots of algorithms there. Many, many fields, support vector machines, ensemble methods. By the way, this company support vector machines. Now you know where the name comes from. It's named after an algorithm, a very dominant algorithm, whose name is literally support vector machines. It's one of the AI algorithms. Somewhere in there is this big algorithm, which is a set of machine learning algorithms. I'll mark it like this. This is your neural networks. And today, we are paying a lot of attention to neural networks because we discover that their structure are far richer than we thought. And people often talk about, for example, something called generative AI. Generative AI is actually a tiny little piece within the neural networks framework. Are we together? There are a very, very, very specific class of transformer models and things that produce this. So this one would be generative AI. So the field is vast. Its theoretical core is machine learning. That's a takeaway. Within machine learning are many, many algorithms. It's a rich world, right, with many inhabitants. The neural networks are getting a lot of attention these days for reasons that we'll talk about. And one of the things we discovered in neural networks is, by the way, generative AI, it's not just neural networks. There are generative methods all over the place. Many classes of algorithms have generative ability, right? But we are these days quite a bit focused on the neural network-based generative models. Right? And in this course, we'll spend a lot of time doing lots of labs, building a lot of things. We will learn to create, for example, the summarizers of text. We will create your digital clone. We will create an AI that talks like you in your voice and speaks in your mannerism. We'll do it in this course. We will train AI to produce quite literally text in the style of any author that you like. We will make it do, besides doing funny things like this. I think in Times of India recently, I noticed an article in which, the day of the AI, I believe it was, in which Shashi Tharoor, who is a person with a flair for language, writes with rather interesting English. You asked AI to write to tell a ex-girlfriend adieu and end of relationship. And it wrote the most beautiful and hilarious piece that you would have sworn comes from Shashi Tharoor. Right? So it gets to be very interesting, but AI does also very practical and useful things. The world, AI is eating the world for lunch in so many ways. But instead of telling you all the things that it can do, let us do those things in the course of this workshop. We will actually build models, practical models. We will do those things in our labs. Are we together? So with that, yes, please.
So how do you differentiate with this learning versus imitating other things? So is there a differentiation between imitation using AI versus learning from AI?
Excellent question. So one question we get, what's the difference between learning versus imitation? Imitation can never generalize. Right? And this question keeps coming up again and again. Is AI nothing but a mechanical parrot? Or is it really learning? and is endowed with intelligence? Simple answer is, all the evidence is it is endowed with intelligence. This is it. You can mathematically measure it. It's called the loss function. And we'll do it in our labs, in our practical. We'll actually do all of those things. In the very next lab, next week, we'll do all those things. We'll start doing those things. Any other questions, guys? Go ahead.
Is this the NLP and the LLM part of the generative AI?
Of course, everything is. Well, NLP is a broad subject, of which generative aspect is one aspect. See, natural language processing has a long history. But suppose you want to generate text as a continuation, which is what ChatGPT is. That's why it's called completion or continuation. Right? That is just one activity within NLP. Another activity is to discover all the named entities. Right? Another is to just classify emotions, sentiments, do things. Right? Categorize it by different subjects. One of the activities that you guys will do, right, in this. So you realize that you have lots of emails. Would you not like to categorize it automatically into a group of your own grouping of subjects and tag them? We learn to do that. Okay. So that's it. Any other questions, guys? Bhavin.
Question. Going back to that, the generic discussion about the intelligence versus the learning or things. So just to take an example of like Newton has invented calculus.
Yes.
So it was not there. So it was that intelligence.
Yes.
Somehow like based on like what's happening in the physical world to try to model it. Right. So
excellent.
Is the AI what we're talking about today? It all
capable of true innovation, true discoveries.
Yeah.
Very good question. I'll repeat it for the remote audience. The question that is asked is actually beautiful. It says that, see, when Newton sits down and discovers the law of gravitation, for example, it is bringing into the world something completely unthought of before, right? And is AI capable of discoveries of that kind? And the answer to that till last year, and even I used to believe, is no. AI, I used to think, is an interpolation engine. It can be creative. For example, if you have played around with DALL-E or image generation, you notice it creates very beautiful, evocative images. It writes beautiful poetry. It writes text. It does all that. But these are within the space of what it knows. And it is mashup of different images and things. So therefore, mathematically, it's an interpolation in a very high dimensional space. Right? But can it actually be creative? Now I change my mind. If those of you who have been attending my weekly paper readings, in the last couple of months, you know, alpha geometry, it is able to prove theorems that I find it hard to prove. Right? It is able to discover solutions. For example, a bin packing problem. Let's take a very real problem. Today, when a shipping container leaves, let's say, China and brings things to US, the one thing you want to do, you pay a fixed price for the shipping container. You want to use the least number of shipping containers. And the last thing you want to do is ship air, empty air. And yet, despite the fixed cost of the container, a lot of the containers are imperfectly packed, a lot of inefficiency. So just bin packing, optimal bin packing has been a problem, unsolved problem. There's the best heuristics that has existed for a long, long time. AI beat it.
But as if that is still, within the learning that you're giving to that system, right?
Yeah.
It's not obviously getting from out of the scope. The example you mentioned, the
No, what is happening is, and for that, as we move along, you'll see, because you give it a creative latitude. In fact, some of you may have noticed that the LLMs, they hallucinate. They cook up things because you give it some degree of creative license to make things up. When you couple it up with a verification engine that checks what it made up creatively is actually correct or not, you actually can go through a journey that is a discovery process. And in fact, one of the hardest problems that Terence Tao considered, and I won't go into that problem, I did that paper reading, I won't repeat it. It started making breakthroughs. It really, advance the state of the art in mathematics. So we are in different times. We are seeing for the first time that these machines are not just giant interpolation engines, are not just stochastic parrots, but they are, coupled with the right tools, they're genuinely able to do completely creative things. Now, well, whether have they reached the level of creativity that they can conjure up the theory of relativity of Einstein on their own without that background, or whether they can do something of that scale? I don't think we are there yet. We are making very baby steps, proving that there is a possibility that we can make it into creative engines.
Is it what called general intelligence?
Artificial general intelligence, yes. So AGI is far, far away. Right? I don't think we have the slightest clue how to go about it. We have created very clever artificial intelligence, but human beings have generalized intelligence. Forget human beings. The little bird has generalized intelligence. Or for example, the crow, we now know, are brilliant statisticians. Actually, much better than most human beings. Right? And so on and so forth. So I won't go into that, but that's that. Any other questions, guys? I'll move forward from that to the next topic. But now comes the crux of the problem. See, with artificial intelligence, we live in very interesting and dangerous times. And this is a topic I'll talk about just for a few minutes. I'm teaching artificial intelligence, right? And neural networks and so on and so forth. Do I understand it? What would be your reaction?
Yes.
Yes. Anybody would like to dissent? Don't have to be respectful, just say openly. Would anyone like to dissent?
It's definitely more than what I do, but there is a scale, and maybe in that scale you're higher than most of the people here. But that scale, we don't know what the scale, the top of that scale is.
Okay. So here's what I'll tell you. There is nobody in the world, nobody at all in the world, who has the foggiest idea how these neural networks really work. We don't know whether they understand things or don't understand. We don't know, in psychologists speak of the so-called theory of the mind, which is that when I talk to you, I have some idea of what you're thinking. I have a theory of how your mind is thinking and taking in my information and reacting to it, right? We used to believe that animals don't have it. I totally disagree. Those of you who are pet owners know that dogs have a pretty good idea, right, of what you're up to or what you're thinking. But anyway, there's a theory of the mind. We used to think that obviously machines don't have a theory of the mind. There's emerging evidence that they have a theory of the mind. They know what you're thinking. They're capable of deception. They're capable of lying. They're capable of changing their answer based on what they think you would like. In fact, we train them like that. In fact, direct, one of the things is reinforcement learning is all about aligning them to produce answers that you would like. But the reality is we don't have the foggiest idea what exactly is going on in these big neural networks. So remember that. We know some pieces of it. The pieces that we know is enough for us to build marvelous AIs. And those pieces is what we'll cover in this course in 3 months. But for everything that we know, there is practically 100x that we don't know, actually. Most of the important things we just don't know. Not only don't know, we don't even partially know. They're just like blank. We are absolutely blank on it. So remember this, guys. Now, I'll give you a historical precedent for this. When the steam engine came, those of you who are history buffs remember that the Industrial Revolution started. The transition from agricultural, agrarian society to Industrial Revolution, the so-called Industrial Revolution, it started with one invention. Does anybody remember what that was?
Steam engine?
The steam engine, exactly. The steam engine was discovered in 1712. It was the Newcomen engine, quite inefficient. And then James Watt, I believe, made it much more efficient in 1769, long, long ago. What did the steam engine do? It produced a perpetually spinning wheel. Once you can do a perpetually spinning wheel, then the rest of that are details, gears, pulleys, etc., to make text. After that, to do various things, isn't it? You could build locomotives, you could build textile industries, you could do all sorts of things. You could craft metal, you could do utensils, God knows what else, right? And so the Industrial Revolution started. But did we really know how the steam engine works? There were some quaint ideas of caloric fluids being exchanged that sort of explained how the steam engine works. We didn't have the foggiest idea. In fact, it took more than 100 years. In fact, before luminaries, physicists like Sadi Carnot created a proper theory of thermodynamics and the Carnot engine, the Carnot cycle, right? And Kevin, and they built it on principles of energy and physics. It took another close to 100 years to really discover quantum physics and therefore have a statistical mechanics foundation that explain thermodynamics and explain what heat really is, temperature really is. And yet we were using heat to create a perpetually spinning wheel since 1712. And the Industrial Revolution had started. So you realize that in history, we have many such precedents in which things we, through experimentation, through hacking, what you would call hacks today, we figured out ways to make things work. And we have some bogus theories of why it works, quaint theories of what it works. Some of it is true, some of it, much of it may, in hindsight, be proven wrong. And yet the world moves on with that. The world transforms. AI is transforming the world, even though we don't understand why it works. Remember that, guys, because through all the remaining weeks, I will be explaining you concepts, we'll be doing labs. It will all induce into you a bias, a misconception that we really know what we are doing, right? I'll be explaining you about gradient descent. I'll be explaining about backpropagation, the attention mechanism, the autoencoder, the generative adversarial network, right? Encoder decoders of the transformer, diffusion models, energy models, normalized flows, right? Convolutional neural networks, everything. And through all of this, I'll explain. But remember, through all those explanations, what I'm explaining is that little part that we know of why it works. But there is a vast amount that we don't know.
Can I ask a quick question?
Sure.
Yeah, hi. My name is Aparna, and it's been interesting that you're bringing parallels between different fields. It's been fascinating for me to listen to your talk, right? Other than just going into the neural networks and then talking through some of the regular AI stuff that I get to see in many courses and then also online, talks. So thanks for that. Thanks for bringing all the parallels from different fields and how they all come together. So you mentioned one thing that's very interesting. What we understand is only a part of the whole thing, right? So I was just thinking to myself again, my mind went in another direction based on what all you mentioned. Say, my brain can be connected to some, because with all the imagery and other advances that we have, if my brain can be scanned, right? And then all the neurons, because our brains are the best neural networks out there. We make so many decisions, we think so many things. If I can model my brain as a neural network through some kind of imagery, and then get a mapping over and over, right? Like how this works. And then what I'm going to do, right, in a day, how I'm going to go about my life, like make decisions in 2 days. If I can predict, obviously there is some model sitting in my brain, right? That is what is
Yes.
from my conditioning, the way I have thought, the thought patterns, like my physiology. If all of this can be mapped to a model, right, through imagery or like through some software, then I have built a neural network for myself, right? And if we build neural networks are the models for each of us, and then put it all together. Is that what this neural networks, this AI business is going to, predict? Because what I can, my solution to a problem can be different from the way you can think of a solution to a problem. So how do we rationalize something is correct or wrong?
That's a very good thing. See, people have been trying, and there's a lot of hype these days that we can create a digital twin, a neural network, artificial neural network, equivalent of the human brain that will think, act, and behave like the human brain. But let me ask this, and this I think is an act of hubris, and this is the old thinking machine kind of thinking, a behavior repeating itself. People are getting carried away by hype. These days, AGI seems to be imminent. If you believe it, tomorrow morning you'll wake up and it will be there. Right? I don't think so. I think these are nonsensical things. I'll explain to you why. We train neural networks for very specific tasks. They do those tasks well. Within a certain boundary, they can generalize well. For text, for example, ChatGPT does pretty well. Ask it to cross the street and see how well it can do it. Right? Today, what we think, how we learn, we are not just learning machines. We fall in love. We have emotions. We have hopes. We have dreams. Right? We have compassion. We are trying to induce some form, some simulacra of compassion into these machines, because if we don't succeed at doing that, humanity is doomed. What prevents these machines from concluding that the most efficient thing to do to save planet Earth, and therefore for their machine survival, is to just get rid of this nuisance human beings who are screwing up the environment? Right? For example, so human mind is a lot more than that. The mind, for example, if you believe the Western, and these are different schools of thought. In the West, people believe that mind and brain are synonymous. Mind is simply the dynamic of the brain. The Eastern thinking is very different. Eastern thinking says a mind is affected by the brain. For example, if you go to sleep, you lose self-awareness. But mind is not the same as the brain. Right? And so who are we? Can we create a digital equivalent? Again, goes back to a mathematical definition. Who are we is not measurable. To the fact that who we are, our personalities, our emotions, our thoughts, is not measurable, it's not empirically quantifiable. Therefore, at this moment, AI cannot reproduce or create a digital you. It cannot do that. I'll leave it at that.
Yeah, that's good. Yeah, thanks for the explanation.
Any other questions, guys, before we move forward? Because now, in the next, we have given an hour and a half. I would like to introduce the first set of machine learning concepts. So I'll just give you a list. For those of you who have some background in machine learning, I will just enumerate. I made a provocative statement. We know something about machine learning, about AI, but there's a vast amount that we don't know. Right? So what do we know? We do know, and I will teach you in the way, maybe today itself, I'll teach you that neural networks are basically engines that layer by layer do two things alternatively. They make a linear transformation, as in the linear algebra sense. What is a linear transformation? Some form of rotation. So, for example, I have this here. I just did a rotation, right? It's a linear transformation. I move it here, it's a linear transformation. I move it there, it's a linear transformation. Or I could do some stretching. I wish I had something to stretch. You can stretch things. That's a linear transformation. Rotation, stretching, moving. These are all linear transformations, affine translations, and so forth. It does that. And then it follows up with distortion. What does distortion mean? You take a page. Well, a page is, you can't. So let me take a real page. Let's say I take this, right? I can rotate it, stretch it a little bit, move it around. And then what can I do? I can do like this. I can do a deformation of the page. I can stretch it out and turn it and do weird things with it. and now it doesn't look like a flat plane anymore, isn't it? I can do a deformation of it. And what we do know for sure, that neural networks have an interplay of just two operations. And I'm somewhat simplifying it, but that's what it is. It is an engine that performs linear transformations and followed by deformations, followed by more linear transformations of your data and more transformations. And successively, it keeps doing that to your data until the data begins to look like the way it wants it to look like. And then it solves the problem very easily. So if it has to tell cows and ducks, it will take all your data points and it will keep on twisting the space in such a way that it creates a new space in which all the cow attributes are on one side, all the duck attribute values are on the other side, right? And it says, simple, now I draw a line, right? Well, it turns out cows and ducks are easy. You don't need to do too much, because if you look at the axis of cows and ducks, this is actually too easy a problem that hardly needs deformation. If I may say, let's say that this is the size of a cow, size of an animal, and this is the weight of an animal. You would agree that all the ducks are light, very small, light things sitting here, and all the cows are big things sitting here, right? Think about it this way. So in this particular case, actually AI doesn't have to do much. All it has to do is, it says, aha, I need to draw this line. This side's duck. Everything on this side, cow. Do you see that? Right? But sometimes it is not so obvious. For example, if I give you all the points inside are positive points, all the points outside are, let's say, negative points. And inside, forgive me if this is terribly done, I will, okay, let me make it this way. Inside is positive points and outside is negative points. And I say, okay, draw a straight line. How do you tell if a point is positive or negative? And it will say, oh goodness, how do I do that? So what it will do is, it will convert that page, which is a board, into, guys, one student is calling. Let me go. Hello, can I call you back? Hello, can I call you back? I'm giving a lecture. So if you look at this bowl, look at this bowl. If the bottom of this bowl was blue and the top of this bowl is orange, can you draw a straight plane cutting through it? Imagine in your mind, there is a plane that will cut through this, such that below that plane, below that height, all parts of the bowl are blue, all parts above that height will be orange. That can be done. And so what it will do is, when you get data like you're seeing on the screen, it will look at this page and say, hey, let me deform this page into the shape of the bowl. Because the bottom of the bowl will be blue, the top will be orange. And therefore I can make a straight plane cut with a single knife's cut. And I can separate the blue from the orange. And that is what neural networks do. They just fiddle around and say, what do I do? What do I do? What do I do? This is what I need to do. And then I'll be able to tell the blues away from the oranges. Right? That is one thing we know about neural. By the way, this is not just an oversimplified explanation of neural networks. This is the explanation of neural networks. This is what they do. Are we together? The next thing is, how do they do it? How do we solve? And there comes a magic called, which has this celebrated name, a gradient descent. Right? It's a mathematical term, but it means something very simple in real life. It is that which you avoid doing when you go hiking. So when you're hiking up a hill, what is the one thing you don't want to do? Take the path of wherever it is steepest, take that path. Because what would happen if you take that path? You'll break your bones and end up at the bottom, right? Imagine that you're on a steep mountain. The steepest part is the one you want to avoid, isn't it? But when you're trying to find a solution, it turns out in an abstract space, which is called the loss landscape. This is a mountain and you want to find a way down. So you take the path actually along the gradient or the direction of steepest descent, right? That a sensible person wouldn't normally take. Are we together? Intuition, right? Does it follow your intuition? Or imagine that the hills are rolling hills, right? Let me get back this bowl. See, guys, if you're at the rim of this bowl and you want to quickly get to the valley, the bottom of the bowl, your choices are you could be going this way, you could be going in any direction, right? But which path is the most sensible to go quickly to the bottom? It is the path of the steepest descent, isn't it? This path. That is gradient descent. Are we together? That's gradient descent.
So should we say it's a shortest path, or is
it is the direction of steepest descent, and it will generally be the shortest path. Now, this is an intuition. What will happen is you sometimes don't do that. You little bit zigzag, etc. Right, and for reasons that you'll understand in that. The other thing is you minimize. I said that learning is the minimization of error. We don't just use the error, we add some more terms to the equation, and we call it the loss function. But one intuition you can carry in your head is you just minimize the errors. It's not too far off, but the right term or the precise technical term is you minimize the loss function. So the learning is nothing but the minimization of the loss function, minimization of the error. And that we know, we do. Now, how do, in particular, so far, there's one more thing. How do networks then learn? They backpropagate, but they're made up of so many layers. Some may learn here, but then how does this guy way back here learn from the error that just happened? It turns out there's a process that was discovered by discovered and rediscovered many times, right? So I'll take the latest, but not the first, but the latest rediscovery, which led to a lot of momentum. That was done by Sir Geoffrey Hinton, right? The person who, as you know, used to head AI at Google and then has now resigned, and he's also a faculty in Canada, right? Not just Geoffrey Hinton and a few other researchers. So that is called backpropagation. How do you backpropagate the errors so that every layer in the network learns from it? We will learn this technique of backpropagation properly. We know that we do that. Now, the biggest thing that happened, I suppose, in recent years, the big breakthrough that happened was in 2017, December, came out a paper, Attention is All You Need. We will cover that paper in great detail. Now, those of you who are taking the boot camp will actually encounter this paper right this Sunday itself. Right? But in this particular course, it is a few month or so away from us at this particular moment. Attention is a specific concept. What is that concept? It is that, so imagine that, so by the way, I go hiking every morning or almost every morning if it is not raining, right? So from my home, which is in Fremont, I hike all the way to the bay, the San Francisco Bay, and then hike my way back. Up and down, it is it's about 10 miles, right? Now, when I go there, I'm not paying attention. The whole point is that is my time, my break from work, from everything. So I'm enjoying the trees, the sunrise. When I go out, the stars are still out. Dawn hasn't started. So I get to see the last of the stars, right? And then gradually the light comes, and I absolutely love seeing all of that, the birds waking up and so forth. So my attention is everywhere. I'm looking everywhere. But what would happen if I suddenly heard, wow? That would scare me, isn't it? My eyes would immediately scan the landscape for a mountain lion. There are mountain lions here. They're relatively rare, but they are there in my trail somewhere. Right? So what has happened now? Am I paying attention to everything or the things that I want to pay attention to? Or attention has completely changed. The context Bila growl has completely changed my attention to that bush behind which I can sort of make out this mountain lion waiting to pounce on me. Isn't it? You see that? So it is not for the whole landscape. It's focused very narrowly in one region of the entire data. That is that differential attention that you pay, the differential focus on one part of the data, the visual field of data, relative to other parts of the visual data field, that is attention, right? When you sit down to study, many things are happening, right? If you all grew up in families, your brothers and sisters are dancing, music is blaring, your mom is calling you for food, right? And getting angry that you haven't cleaned your room, right? And many, many things are happening. But you have an exam tomorrow. So your eyes, your whole mind is focused on a very narrow visual and audio field. What is that? You are able to eliminate everything and focus on the book. Hopefully, right? That is attention. And that is that discovery that with that you could create actually pretty powerful autoregressive models, or models that could do things that a prior architecture RNNs could do. Yeah. And you could do it with just attention only. That's why the title of the paper, Attention is All You Need, was a major breakthrough. Those researchers found out it also removed a major bottleneck in compute. You could now do things in the whole sentence, the whole text in parallel rather than one token at a time, one word at a time. You could do processing. A whole sort of bag of problems got solved. And that paper, right out of the gate, achieved state-of-the-art results in natural language processing in many domains, many problem tasks, 6, I believe. Despite the brilliance of that paper, even the creators, and I would obviously, it's a presumption, I don't know because I haven't talked to them, but all the evidence is that even they did not realize the full importance of the breakthrough. It was a computational efficiency, it was a good breakthrough, came out of Google, but it took people a long time to realize that, oh gosh, this attention mechanism is insanely powerful, right? Why it works, we still don't fully understand, but we do know that it works beyond our wildest dreams almost. And out of that attention, self-attention, came an architecture called transformers. And when you use the word language model, a transformer is a language model. Language models are type of transformers. And large language model just means that you make it bigger and bigger and bigger, right? But there is a lot that we don't know still, and I'll come to that. And then there are convolutional neural networks. Convolutional neural networks is about receptive fields. Once again, which part of your eye is paying attention or looking at which area of the visual field, right? It turns out it was a lot of these ideas arose from studying the brain of cats and the visual cortex of cats. But convolutional neural networks have been there, we'll study it. So these are all the things we know. And there are many such things that we do know, but there is a vast amount of things that we actually don't know. In fact, some things goes against 100 years, almost 100 years of statistical wisdom, right? Or 100 or 50 years. Let's be conservative, 50 years, right? Or 30, 40 years of statistical wisdom. But one of the wisdom is, if you open any textbook on machine learning, it will tell you about the bias variance trade-off. Has anybody in the audience heard of the bias variance trade-off and would like to explain what that means? Anyone?
Bias means actually it fits the model. So variance would be little kind of overfitting or something like that. Some errors in the system.
Mani, yeah, good answer, Prashant, but a little off. Prashant, go ahead.
Bias is overfitting. They are fitting more to the data. It's opposite.
I wonder.
Go ahead. Somebody, I think I heard a female voice in the audience.
Yes, I wonder bias is based on the data, right? For example, the training data can be, leaning towards certain things, right? And so maybe the model predicts things certain way, right?
Oh,
For example,
no. This is not the ethical bias or the societal bias. A bias in statistics has a specific meaning. It is like a systemic bias. You know, you're measuring equipment. Always measures 3 degrees lower.
So,
Please, like,
the bias
Data is more,
variance.
the data is more connected to one way.
No. So, can I try?
please go ahead, Heidi.
Okay, bias and variance trade-off describes the relationship between the model's complexity and the accuracy in its predictions. So it's ideally both should be low. We find the sweet spot for choosing our model.
Okay, guys, you heard the voice of one of our teaching assistants. She happened to answer it correctly. I hope it reinforces the message. Whenever you're stuck, reach out to her.
What's that name, please?
Harini. Very good.
You
Very
know,
good.
why would they call it bias though? Because
Now, I'll explain what it is. It's actually, it has to do with the community of statisticians. So I'll explain what bias and variance are. But I'll explain it in an intuitive way rather than a mathematical, algebraic way. See, what happens is your data. Let us say that your data, I'll give you an example. Let's illustrate it. Let's say that this is your data. By the way, this is actually a data from your lab. So you'll do this lab and it will all become very real for you next time. Imagine that you're looking at this data, right? This is X input, this is Y, right? You're supposed to predict Y as a function of X. So this is a regression model. Y is some function of X. Now, you can hypothesize that Y is a straight line function of X, right? You can say, hey, this is the relationship. And if you try to fit a line, the best fit line that you can fit is this. You'll see it when you do the lab, you'll see it. This is about as close as you can get to fitting the best line to the data. At that particular moment, your model is too simple. Your hypothesis is too simple compared to the ground truth, isn't it? So this is a biased model. The word bias comes from a bias. It has bias errors because of a statistical term, which has nothing to do with societal bias and other things. It's just a historic word that has stayed in statistics. Then the variances, suppose you make a model like this. Now look at this blue model. What about this? It is making a hypothesis about the function that is way too complicated. Would you agree? And it is also missing the mark big time, right? So you say this has variance errors, and because there's a quantity called variance, which is x. Variance is the square of standard deviation in some sense. X minus x mu, or the mean of mu squared, is adding it all up as your variance. So, but let's skip statistics and stay with intuition. So you can see it's making huge errors. Now, if you make a third model, which is, let me take a different color, some form of green, let's say. All right. Suppose you make a model between the blue model, the pink model, and the green model. Which do you resonate with more? Which is closest to the data? The green one, isn't it? So you say that green one, see what happens is when you go from the pink one to the green one, the bias errors go down, right? It becomes less biased. When you go from the blue one to the green one, the variance errors go down. Now the total error in a model, and this is something I'll just mention, the total error in a model is the sum of bias errors. Actually, the technical word is bias squared, but I will just call it bias errors, variance errors, plus something called irreducible error. Let me talk about these three quantities in particular. The bias errors is the errors that come because your hypothesis is too simple, too naive compared to the ground truth. Variance errors comes because you have created too fanciful a theory, right, compared to the ground truth. The irreducible error, what is this irreducible? It's the error that is made up of many things, but it is made up of that which you don't know, that which the model simply doesn't know. I'll give you an example. Let's take the example of a young entrepreneur selling ice cream on a beach. The young entrepreneur gets data which says temperature, X is the temperature, and Y is the ice cream sold. Now you realize that on cold, windy days, you won't sell much ice cream. Kids would be freezing, parents wouldn't bring them to the beach, right? But on warm, sunny days, you would sell a lot of ice cream, right? So you're making a function Y of just X, and you will get you may make a good function. You may do a good bias variance trade-off and come up with as close to ground truth as possible. But what is missing in this picture, guys? Do you think as a young entrepreneur, you can make a model of how much ice cream will sell on the beach purely on the basis of temperature? What else is missing? Roman?
The amount of people, the population.
Yeah, proximity to the, for example, population center, how much of a drive it is. More importantly, windy, is it windy? Right? Things like that. Is it a work day or weekend? Who brings kids to the beach? Parents do. Parents are rather inaccessible during the work days, isn't it? So there are many factors which the data doesn't represent. So the missing information is causative of some of the irreducible errors. Are we together? It is that which the model cannot know because the data isn't there. The missing factors. So whenever you build a model and you have a huge irreducible error, it should be a clue that you missed something important. Maybe wind, maybe day of the week. Other important factors are missing from your data set that you should need to make a good model. The other aspect of that error is pure instrumentation error. Like, have you noticed that every time you stand on the scale to take your weight, you don't like it, what do? You shift it a little bit and stand on it again. And maybe next time you like the reading, right? So that is an example of instrumentation error, right? Those of you who use a thermometer, laser thermometer, point it at the same wall, same device. Do it over and over again, it will keep changing its reading. Those of you who measure your blood pressure, you don't like the value now, just take it all over again. You'll like it better next time. Or maybe not, right? So that's instrumentation error. Yeah. Irreducible instrument, because every instrument has an error bar associated with it, right? So that also captures into the irreducible error. So now, coming back to the thing that I was going to talk about, a very interesting phenomenon called double descent. By the way, I've asked you guys to read about double descent. It's a mystery. No one knows why it works. So what happens is that, let me explain what happens. Suppose you make a graph, model complexity, and how much total error you have, total error. What happens is that, let us say that there is some ground truth. This is the real complexity of the causative forces, right? Think of a degree polynomial of degree, let us say, for a sine wave, a degree of 5 would be pretty good, right? So what will happen is, when you make a model that is very simple, you'll have huge bias errors, right? Then, and this is your test, by the way, test total error when you validate it on the test set, and then unseen data. And then what happens is, if you go on making complex mistakes, complex models, now you start accumulating variance or overfitting errors, and this will start shooting up, right? So what do? You draw it out for different, you call the model complexity the hyperparameter of your model. You dial it in back and forth to see where do you achieve a minimum. And that's your best model. Are we together? But there is a mysterious thing that happens with neural networks. This is the classical regime of statistical learning. Pick up a book, Introduction to Statistical Learning, ISLR, the classic. And I have taught you guys from this book in the past. Pick it up, you'll see this curve. This curve is the most celebrated curve in machine learning. It's all over the internet. But then comes, so so you notice that the error descends to a minima, right? And then it blows up. You expect it to blow up, right? Common sense says that you keep on making models, overfitting the model, you'll get this blue line behavior, huge oscillations and big variance errors. But with neural networks, something very mysterious happens. And no one really understands why. There are all sorts of hypotheses and theories about it, but nobody knows for sure. What happens with neural networks is, in neural networks, you make the model more complex by throwing more neurons, right, etc., etc. And I'll give you a simplified picture today, model complexity. You must be hearing, if you download these LLMs, oh, this is a 1 billion, 7 billion parameter model, this 13 billion, and you scoff at it. It's such a tiny model. Let's go with a trillion parameter model or something like that these days, right? So it's pretty fashionable to talk like that. But if you look at the error, test errors, we notice something quite mysterious and nobody knows why. This thing will happen. You have this minima and you're in the classical regime and it will start shooting off. But weirdly enough, as you make the model bigger and bigger, and for reasons that's not very clear, it reaches an inflection point and it again starts going down, right? So you say, what just happened? I made a model that is way over parameterized. It has way more parameters than the data that I have to train it. The common statistical wisdom says that you cannot have more parameters than the data, because then it will exactly fit the data. But what it happens is you train it with the trained data. For training data, yes, but for test data itself, unseen data, where it is not supposed to work at all, this neural networks, for some reason, do this. Now, there are many hypotheses, some plausible. One plausible hypothesis is that these neural networks, even though you made it very complex, the complexity just gives it flexibility to rediscover a simple function, a much more simple narrative flowing through the data. Are we together? It's a very interesting statement that, in a sense, when you make the model so over-parameterized, the neural networks have some sense of internal self-regulating behavior, God knows from where, that causes it to discover a very simple and elegant mathematical function that really represents the ground truth, right? And because of its discovery of that, it sort of, again, has very low errors, right? So this phenomenon is called double descent. On the course portal, I've given you guys links to it. Please watch the interview. One of them is an article. The other of them is an interview of Jan LeCun, one of the great fathers of this field. Yeah, and of course, the head of FAIR, the Facebook AI research.
Is that a hypothesis or a...
It's a fact. It's an observed fact. And we don't know. See, if it was a hypothesis, we could say, this is wrong. The problem is it's a fact and we don't know why. Right? The other such thing is generalization of deep neural networks. Again, the same point. You're not supposed to be able to generalize when you throw so much. You're supposed to exactly fit. You're not supposed to be able to generalize or learn anything at all. You're supposed to just memorize it. Right? And yet, these machines are able to generalize despite being over-parameterized. I mean, look at it today. In the modern AI, you download a big model, a transformer model, and you fine-tune it with barely any data, right? We have one person in the audience who's fine-tuning it with a bare 50,000 rows. Well, you say 50,000 is a lot of rows. Why are you saying it's not enough? Well, it turns out that model was pre-trained with gazillions of rows, hundreds of billions of data points. So 50,000 is a drop in the bucket. Why in the world is it able to learn anything at all for so few? But 50,000 itself is too much. You can often train it with just 100 rows. What gets even more mysterious, really mysterious is, and we don't understand, why can we train sometimes with just one or two examples? right? How can you fine tune it or sometimes get it going with this? And people have done some very interesting experiment. So, you take images and you give a label. This is a cow, this is a duck, this is a horse, right? And you train it and then it can classify images correctly. You expect that, isn't it? Because that's what you taught. You said this image, when you see images like this, remember it's a cow. But one researcher did an interesting experiment. What he did, I think, or she did, is she went and randomized all the labels. So images are there, but irrespective of, even if it is a cow, it's called a zebra. Some other place, a cow is called a pig or something like that. All of the labels are jumbled up. And then you train the model. And peculiarly enough, we don't quite understand. This model still manages to learn. Right. So there is something very deep going on that we don't quite understand. Right. Go ahead.
So is this the double-digit for both RNN on CNN?
All neural architectures.
All neural architectures. And
Is
so
there.
that means the ideal model is that minimum place, right? So we are going to have a two minimum.
Yes, that's why it's called double descent.
So we have to, every time you have to work for the second one.
And usually we consider the second one a better model because simply because it somehow is doing more things to it. Yeah, it's more generalizable. Other thing is neural networks, we think that they are learning representations. The idea was that they learn internal, deeper representations. Like, for example, I give you an example of the bowl and that picture, right? That it will create a bowl and say, hey, the bottom of the bowl is blue, the top of them is orange. I made a bowl out of it. But does it tell you that it made a bowl out of it? Sometimes you can see it. Most of the times you have no idea. Because these neural networks are thinking in literally hundreds of billions dimensional spaces. We are not, you and I can't think in 4 dimensions. Right? So here's a little thing. When I was doing mathematical physics, we would talk like this. As is obvious in 11 dimension. And the other person would say yes. The point was it is not obvious. It's just mathematically obvious because none of us can visualize 11 dimensions. But we know that the mathematics works out. Right? So it's just a way of saying. Right? Superstrings are in 11 dimensions, 10 plus 1. Right? So that's how it used to be. Now, we are creatures who can't even think in 4. These machines are doing gradient descent. They are building these bowls, representations in billion dimension spaces. We don't have the foggiest idea what they are doing. Because even if they told us the representation, we wouldn't understand. And they don't tell us. Right? That's how it is. How do they? One of the peculiar things is that a neural network is just made up. Is someone asking a question?
Yeah, can I ask a quick question based on what I heard? Again, trying to map this entire course material, right? This is my problem statement. So I went to India recently and I was stuck in a traffic jam, right? So pretty much everyone was using Google Maps, right? To get from point A to point B. And then there were these big congestion points, traffic congestion points. So as I was thinking through this, right, obviously there are other infrastructure and other improvements that need to be made, right? Leaving that, how can Google Maps give out some kind of smarter maps, not the shortest location, right? Shortest distance, because as one of the algorithms you went through, you said it's normally the shortest distance. But if I look at it from a spatial point of view, right, you and I can get different maps, but our goal is how can we get there faster? So maybe I'll take a bit of a detour and you take some detour. The goal is not to have that congestion and lose time. So in the AI, AI space, right here, the different algorithms or models you have. What is that model or algorithm that can be used for this kind of a thing?
Oh, that is actually simpler than you think. Those are
really?
Those are graph algorithms and a bit of graph neural networks. And if you stay with us, especially if you were joining this boot camp, you would one of the exercises would be very similar. Yeah? So
but it is not about the shortest distance, though.
No, it is about the shortest distance, and it is not. See, what happens is that you change the definition of the shortest, right? And you say that the length of the edge between 2 points is proportional to the time it takes to go from here to there. And that the time is a function of multiple variables, and you build a model for that.
Oh, I see.
It can be done.
So the weighted graph kind of a thing?
It is a weighted graph, except that the weights are computed using interesting algorithms. Yeah.
Yeah,
So,
because I know the shortest distance algorithms. So I never thought about, right, that the weight can be just something else. And, yeah.
That's it.
Yeah, okay, sounds good.
Nice. Next thing that we don't know, and we are almost done, I'll just close with a couple of more things. I want you to feel that we don't know, so that there is some work left for you to do. See, at one time it got into my head that I should do some theoretical physics. I went in there and I realized that all the easy problems were solved. And that is profoundly depressing to a researcher. A good day is when you find that most things are unsolved. So in AI, we're having a good day. Most things we don't know. Leaves a lot of good opportunities for everyone here. One of the things we found, I don't know if some of you are following this New York case against OpenAI, New York Times.
Yeah.
What they showed is that you could make OpenAI, give it prompt, and it would literally regenerate their copyrighted content. OpenAI's defense was, Milord, we are not memorizing it. My models are not memorizing it. It's just made up of mathematical weights and biases, floating point numbers. Look here, there is no text there. I presume that's a simplified version of the defense. The problem is, actually, these neural networks, for ways that we completely don't understand, manage to memorize a lot of things and hide it somewhere in their parametric memory, in their weights and biases. How do they do that? We don't have the foggiest idea. But we do know that they can regurgitate important sections of information. Right? So that is something that itself is an open question. Then comes...
Isn't that the weights for each of the words?
It's not as simple as that. And so as you take the course, you'll get more intuition into it. Then there is the optimization landscape. People used to laugh at neural networks and say it's a doom thing. Much of the machine learning community, because of a very simple reason, you can do gradient descent only when the loss surface is like a bowl. It's easy to find the minima, tumble down to the minima. But in a world of hills and valleys, you may tumble down one hill and end up in a valley that is way up there in Tibet, right? Way higher. You haven't still reached the Indo-Gangetic plains, for example. You haven't reached the true minima. So in a world of hills and valleys, any valley, any minima you come to, you have no guarantee that it is right. In fact, one would say intuitively that you're most likely to be trapped in local minimum. Right? And yet we know that somehow these neural networks are pretty clever at avoiding those. And they do end up with very close to the real minimum, or effectively the real minimum. How do they do it? Right?
Dimensions.
Yeah, there are dimensions. They have a way somehow to tunnel through and do it, but we don't understand the whole reason. And so for that, I would like to, with that mystery, I would like to end this course with a beautiful visualization that I will do. And there are more mysteries to it. For example, I can poison a neural network with small change data. I can show it a picture of a panda. This was a paper, I believe, again, Nico and Ian Goodfellow and so forth, one of the legends. He showed a few years ago that you can take a picture of a panda. Ask AI, what is it? It will say panda. Then you put a little bit of a noise that to human eyes is not visible. Minor perturbations of the image pixel. To human AI, it's absolutely a panda. Now the AI says, no, it's a gibbon. It's a completely different animal. Right? So you can do adversarial attacks on this. Why those attacks work? We don't understand. Today, for example, the artistic community is up in arms because AI companies have taken their images and they consider it fair use if you put it on the web to train the AI on it. They disagree, right? Because now AI can produce better art than them. So what they are doing is they're using softwares like Nightshade to poison the images. So if it is used to train the AI models will get screwed. That's an adversarial attack on the models.
Watermark is for that's different. Watermark.
No, it's different. It's literally poisoning it in imperceptible ways. And so there are these adversarial attacks, and nobody knows how to defend against it. And what is the whole dynamics of the attack? We don't understand. Why it happens, we don't understand. We don't know what is the why creating deeper and deeper neural networks leads to better results. We really don't know. And how to design a neural architecture, we don't know. Neural architectures can be wide, can be deep, right? How many layers, how many nodes, nerves and neurons in each layer, right? We don't know. It's all hack. If it works, as mathematicians often say about the AI community, when something works, then post hoc put an explanation and make it look as though you knew exactly what you were doing, right? So there's a lot of that. Why does attention work? The transformer, this large language models came out of one idea, and it's working beyond people's wildest dreams. But why does it work so well? Nobody knows. Right? So these are the mysteries, and I'll end today with that. But I would like to end with a visualization that I think is worth seeing. And I hope, hopefully, that will convey to you the beauty of this elusive, mysterious world that is the world of neural networks. So let me end today with a visualization.
We're leaving with more questions than answers here.
If I leave you with more questions than answers, as an educator, I've done my job. To answer, when you leave with answers, learning stops. When you live with questions, the mind is continually learning. Right. Let's go to this thing, lostlandscape.com. By the way, I've added it to your course portal. Everything that I'm talking, actually, why don't I go through the course portal? I'll remember the UI much better. And again, those of you who are guests, you too are welcome to have access to the course portal, but only for 3 weeks. So if you go to the course portal, guys, today was day 0. Do you see day 0? Now you will understand why I titled it this way. Empirical Wonders and Theoretical Frontiers, the enigmatic journey of neural networks. It's a mysterious journey. We don't know it. We are dealing with a mysterious thing that's taking over our lives. For better or for worse, there are risks and there are exciting things happening associated with it. So, guys, actually, I would like to end, if you will bear with me, I would like to do 2 things. One is an exercise that I want to give you. We'll start with this exercise actually next time, but for today, let me just do this much at least. Let's see if we can get to the last landscape. Yes. So let's go to explore. And I want all of us to do this, but later. Guys, do you see this beautiful, beautiful thing? This beautiful thing is what you call the error surface or the loss surface in learning. And all of machine learning, all of so-called intelligence, artificial intelligence is to start somewhere here and find your way to the bottom, where this is the point of least error. This is where your model is fully trained. But to make your way here, do you see how many hills and valleys there are? It is not obvious. It is not shaped like that beautiful, the bowl that I showed you, right? And you can do that. Let's, I believe this is the one. Click anywhere on the landscape. Let me do that. See how it is climbing its way down. Oops, what happened? It got stuck, right? If you're not careful. And then there are things that you can do. There are learning rates. There are many variables. I'll let you play with those variables. And then, oh, what happened? Despite being trapped here and there for a little bit, it managed to somehow bounce out of that and find its way to the minima. Do you see it, guys? You are literally seeing the learning of machine learning take place. This is gradient descent. This is machine learning. This is AI.
So the lowest point means the total error is less.
Minimum. And that is what you can say. You can never eliminate error. When you build a model that makes the least amount of mistakes, you say, I've trained the model as much as I can from this data. What remains is the irreducible error. Right? So, or if your model is too complex, it will have some bias error, some variance error, some other, etc., etc. Right? But there are other aspects to it. But yes, you'll never get to zero error. Now, do you notice that it is stuck here and it's bouncing around at this particular moment? And then you have to bounce it out of there somehow. And then here we go. And you'll learn what all of these parameters are, how to go about doing all of this. But we'll keep that for another day. Now, if you guys will humor me in the course portal, I have also put something else. Let me open. By the way, this is your textbook. When you go to the course portal, you'll notice that I've given you guys some assignments to do. We haven't covered much territory, so these assignments are suggestive rather than prescriptive at this moment. Today was lecture 0, so it was at a high level. Next time we'll get down to brass tacks and start doing more practical, real things. So if you go back to day 0, this was lost landscape. I want you to go to, so your assignment is play with lost landscape, do this reading assignment. Those of you who are programming inclined, please get started with PyTorch. It's a library which we'll use for coding. Are we together in this course? Now, there is something called Play with Tensor Playground. Let me show you what Tensor Playground is. This is it. These are the layers of a neural network. You can take data, let's say simple data, and you can say, well, by default, X1 and X2 are the input. How do you separate the blues from the oranges? Right? You can make this guy run. This is a run button. If you run it, it almost immediately finds the separating boundary. So you notice that any point in the orange region is orange. Any point in the blue region is blue. It does a very good job. Now, will it do such a good job? What is the minimum network I need to do such a good job? What happens if I make the network smaller and smaller and smaller and smaller? Will it be able to do that? It will be. So this is the simplest network that can solve this problem. But will this simple network solve another problem? Let's say, will it solve this problem? Let's try a luck. Not really, because it's trying to draw a straight line, and there is no straight line that will separate the oranges from the blues, isn't it, guys? As you can see, it's making a lot of mistakes. The orange region contains a lot of blues. Right? You could then say, all right, I'll add some more. Now what happens? Look at this. It's able to solve it. Let's try a different example. This one. This is like the example that I gave you guys, right? Let's see what it takes. Can I solve it just with this, with a straight line? One neuron will make a straight line. Well, straight line isn't cutting it, is it? What happens if I add one more neuron to it and try it? Is it doing it?
Still error, a lot of errors.
Still a lot of errors. Now, the reason for that is you need to lift it to a 3 dimension. Remember, the page has to become a bowl in 3 dimensions. To create 3 dimensions, I need one more neuron. I'm going to add that neuron and see what happens, how quickly it learns to deform the landscape. And you have to give it some time, but it will get there. And by the way, tan H is a bit slow. I will take something that's a little bit faster. There we go.
Whoa.
It immediately caught out. What did it do? It literally made a bowl out of your data. Right? So guys, go. This is your assignment. Go play with this. Right? Have fun. And I'll get back to the course thing again. I should have made it such a way that you can't get out of it. getting back to the course. So remember, day 0 contains your assignments. Please do that. I put all the textbooks and all the resources here. Zoom link is here. The 3 blue, 1 brown video channel is here. Oh, I should also add the Support Vectors YouTube channel. So this session is being recorded. And PyTorch, please do get started. Remember, we are a whole team here waiting to help you. Very bright people. Then this is your reading assignment. Let's see what it is. It says, go read the first 3 chapters of the textbook, Understanding Deep Learning. Now, guys, I have said for this book, it doesn't mean that you will like this book. Whatever book amongst the book that I've suggested that you like, read a few chapters from that book. Does that make sense, guys? It is in preparation to the next lecture, because the next lecture will get down to nuts and bolts. It will become very practical. Yeah. So from that, also I'll be releasing quizzes. When the quizzes come, please do take the quiz, right? And you will notice that this video will show up there. A summary of the video will show up there. Quizzes will show up automatically for self-assessment. Please avail of all these education resources. With that, I'll end the formal and the recorded part of this today's session. I hope those of you who are here for the first time, thank you for being here. Welcome. And I hope you enjoyed it.